Okay, we start the next lecture on particle identification. We have already encountered many detection principles by means of which particles can be identified. Let me remind you of the detector layout that is conventionally used in many collider experiments with the tracking detector, electromagnetic and hadronic calorimetry, and the muon system. How can now individual particle species be identified depending on the signature that they leave in the detector? One case is relatively simple. It is the muon. Muons are the only charged particle that can penetrate the hadronic calorimetry. That means it can reach the muon system even if that system is outside the calorimetry or even the magnet. So muons can be relatively easily identified. A second species of particle that can be identified surprisingly are the neutrinos. Neutrinos are weakly interacting particles and they leave no trace in the detector. Consider as an example the event in the top left. What do we assume that has happened here? Let me give you an example of a typical high energy process, the production of a top quark pair that is currently under investigation. We assume that, let's say, a gluon from the left and a gluon from the right produce a pair of top quarks. A top quark will always decay in a W boson. So let's say these are gluons. That's a gluon. That's a top quark here. W boson may decay into a lepton and a neutrino, a p quark, another p quark. I do not write the charges here. And the second W boson decaying into a quark, pair. That's 6 particles in the final state. Forgive my handwriting. And it is what we think has happened in this event. We have 2 B-tagged jets. We have a muon and we have other jets coming from the W boson, so from the quarks from this W boson. And then there is missing energy in the transverse direction because there is the net sum of the transverse momenta is 0 because the protons do not have a net momentum in the transverse direction. So will the final state particles. The final state particles' transverse momenta will average to 0 unless there is a neutrino leaving the detector undetected, and its momentum will align with the missing energy. The event shown to the right is a beautiful top quark pair candidate event with a muon, 2 B jets from W, and the neutrino momentum reconstructed. Now we cannot know whether this truly was a muon. However, all the features of that event that's shown here point towards the production of a top quark pair, and that predicts a muon. So in this sense, even neutrinos can be reconstructed. Now that's a different story, of course, if there's more than one neutrino present in the event, because then the invisible momenta add up and we have an under constraint system and we can no longer reconstruct the neutrino momentum. So next are electrons. Electrons are difficult to distinguish from hadrons, except for their different calorimeter shower parameters. So an electron will shower in the electromagnetic calorimeter. Hadron kaon here, for example, will shower in the hadron calorimetry. However, I've explained in the last lecture that the electromagnetic calorimeter still is a hadron calorimeter for the hadrons, albeit with only about one interaction length. And hence, a hadron can also interact already in the electromagnetic calorimeter. If we are lucky, then the shower that develops from the kaon is long and deep, because that's possible for a hadronic for an hadronic shower, and then we can discriminate it. The shower for an electron is always short. But that need not be the case. Sometimes a kaon can shower in the electromagnetic calorimetry and then look quite similar to the electron. In that case, the discrimination between electrons and kaons, pions, and other charged hadrons can become pretty difficult. The third way of identifying, the next way of identifying particles that we can discuss is when they are long-lived. Long-lived particles appear via the reconstruction of secondary vertices. Let's look at some picture. Long-lived here means picoseconds, so 2-3 orders of magnitude longer than the time scale that governs the collision of the protons, which is 25 nanoseconds. So particles with a picosecond lifetime moving at the speed of light can travel millimeter distances that can be resolved in the vertex. It's important for the reconstruction of, look at the transverse plane here, with the primary vertex, with the secondary vertex. In order to identify the secondary vertex, we need to reconstruct the track of the candidate particle in the most precise way, because what's limiting the resolution is our resolution of the impact parameter. That's the quantity d0, which is the distance of closest approach to the primary vertex. We need to know how likely it is that that track really came from the primary vertex or from the secondary vertex. With the current precision in the tracking at high particle momenta, the limiting factor is actually the interaction in the beam pipe material. So if that is the beam pipe here, the multiple scattering of the candidate particle from the secondary vertex, this can be a pion, for example, leads to a resolution in the parameters of this track, and hence, as the shaded area indicates, hence an uncertainty in the impact parameter. In lecture 3, we ran the numbers for a 5GeV pion example. For secondary vertex identification is particularly critical in experiments that target the physics of B mesons. For example, the LHCb experiment. Here, that example shows a primary vertex that's shown here at the pink dot. A B sub S0 and neutral B meson is created that decays at the secondary vertex that is shown here. And there's even a tertiary vertex from a hypothetical D meson, and the decay chain that's being reconstructed is shown here. So PP makes a B meson, makes a D meson plus a muon, giving the secondary vertex, and then that further decays into 2 kaons and a pion in the tertiary vertex. This event was reconstructed early in the data taking, and the arrow ellipses here show the uncertainty in the position of primary vertex, secondary vertex, and tertiary vertex. So with these decay vertices reconstructed in full 3D, one can, and the charge measurement of the pions and the kaons and the identification of the muon, one can with high accuracy reconstruct the full decay chain. That's one way to identify particles present in the decay. So let us next look at ways to distinguish between particles. Long-lived particles that are stable within the detector can be indirectly identified by their mass. So let's talk about, for example, electrons and muons. Electron is 511 kiloelectron volts of rest mass. Muon is 200 times more. Pion is 140 keV. Kaons are around 500 MeV. And then protons and neutrons around 1 GeV. So we talk about particle masses that enter the particle masses between the 100 MeV and between the 1 MeV and the 1 GeV regime that are useful for discrimination. It's difficult to have resolutions that allow measurements with that precision when the detector is actually built to explore the TeV scale, which is 3 orders of magnitude higher. So we collide protons with 13,000 GeV, then many particles appear through parton shower and whatnot, which partially have tens of GeV of energy, and then we need to discriminate masses in the MeV regime. So that's the reason why the high energy physics general purpose detectors typically do not discriminate, for example, between pions, kaons, and protons. For ATLAS and CMS, these are just charged hadrons. We simply cannot distinguish these. So how can it be done in principle? In high energy experiments, one of the measurements that's always done is the momentum. So let's assume we have a momentum measurement of a charged particle, for example, from a tracking measurement. The momentum of the charged particles is derived from the curvature of the particle's track in the magnetic field, which we've discussed in lecture 4. Now we need a second measurement to calculate the mass. A second measurement is a variable that needs to depend on the particle velocity. And if we want to measure the velocity of a particle, we can measure the time of flight. The time of flight of a particle will give us the velocity. We can use the energy loss in a medium. We have learned that in the Bethe-Bloch formula for the energy loss, the energy loss depends on beta times gamma. So that depends on velocity. Or Cherenkov and transition radiation depend on the relativistic gamma factor, which is also possible, from which we also can infer the velocity of the particle. So velocity measurement, in addition to the momentum measurement, allows us to derive the momentum. On the other hand, we can also use calorimetry, because then we'd have the energy. And by combining, let me underline in the momentum and in the momentum and the energy momentum relations what we know. So let's say we know the momentum from a spectrometer measurement, and then if we know, for example, the velocity, we can compute the mass from the relativistic formula for the momentum. Similarly, if we know the energy and the momentum, we can also compute the mass. As I've tried to explain before, the problem is not finding detectors that are in principle suitable for that measurements. The problem is to have a sufficient resolution in these measurements. That's the real challenge, and that's limiting. So let's look at methods of particle separation. One particularly difficult difficult case is to separate pions and kaons. Both are hadronically interacting and have masses that differ by a factor of 4 or so. And we show here the necessary detector length versus the momentum of these particles for different measurements that could be undertaken to separate pions from kaons. We'll discuss a few of these. We'll begin with time of flight. A time of flight measurement really only works for the lowest momenta around 1 GeV. Once we exceed the GeV regime, the necessary detector length to separate pions and kaons becomes unmanageable small. Unmanageable large, tens of meters, and then growing with the square of the momentum. That doesn't mean it's totally unfeasible, but the typical detector applications will just not work with size requirements like this. In the 10 GeV regime, threshold Cherenkov counters will work. If the energy is higher, then a differential Cherenkov measurements can be done. And for the highest energies, we can use transition radiation. Remember the probability that a charged particle, when it transits two detector regions with different refractive index, emit a photon is proportional to gamma. And that can be used to separate pions and kaons and also to separate electrons and pions. In turn, I think it's clear that this means we need different methods for particle identification for the different momenta ranges. There's unfortunately not a single detector that can be used. Let's start with the time of flight measurements. Time of flight measurement is really something very simple to understand. Let's say we have two scintillator plates with a good timing resolution, okay? One left, one right. Particle goes through here from left to right. Let's say we know its momentum. We want to know its mass. In particular, we want to differentiate two different particles. It's a simple detector. The particles traverse a constant length. All that is needed is a logic that measures the time difference. So let's compute the time of flight of two particles with the same momentum, but which have different mass. The time difference is the length of the detector divided by the velocity. That's it. There's nothing else to it. Now, in the next step, we replace the reciprocal value of the velocity here by the relativistic expression that relates it to the momentum. So we get the square root here with 1 plus m1 squared c squared over p squared. There's a difference because we are only interested in the time of flight differences between two hypotheses, namely, let's say, the pion and the kaon hypotheses. That's two square roots here that we can Taylor expand in the ultra-relativistic limit where p squared is larger than m squared. The time difference then becomes the mass difference squared divided by the momentum difference squared. So if our timing detector has a constant resolution, maybe let's say 0.3 nanoseconds, that's the resolution of our timing, then unfortunately the length that's required to achieve a separation power grows with the square of the momentum. It does not grow linearly, it grows with the square. Let's look at some numbers. The diagram to the right shows the time of flight difference between different particle species, that's for pairs of particles, for a flight path of 1 meter, okay? So this is normalized to 1 meter, which is already a very sizable detector. Let's look at the middle curve. That's for pion-kaon separation. We separate pions and chaos. We want to separate it with 4 standard deviations. That means if our timing resolution is 0.3 nanoseconds, which is really good, we want to have a difference of 4 such units, so that we only rarely make a mistake. In this case, roughly 1 in 10,000 times we make a mistake. So let's say that should be the quality of our measurement. That means we need a time of flight difference of 1.2 nanoseconds. If you look at the curve and you take the 1.2 nanoseconds and you use this formula, you find that you need roughly 3 meters for a momentum of 1 GeV. In other words, if you have pions or kaons at 1 GeV and you want to discriminate them with a resolution of 0.3 nanoseconds and you want to, on average, see a difference of 4 such 4 sigmas in the timing resolution, the detector must be 3 meters. Well, you can probably build this, but if you then want to do something else with your detector, for example, investigate a different process, and you need to separate pions and kaons at 2 GeV, then the length would be 12 meters, and that's unfeasible. Hence, for the lowest momentum, time of flight measurements are doable. For higher momenta, it's not possible. That's why they are rarely used in high energy physics experiments, and they are more frequently used in nuclear physics experiments. Good. Let's look at multiple ionization measurements. That's a completely different process, completely different feature in detector physics that's exploited here. And in fact, we've already discussed it in lecture 3. So here we are interested in the energy loss of particles, that is the DEDX, as a function of the momentum. We consider charged particles that are heavy enough that the ionization is dominant. So the only species that's excluded is electrons. Electrons are too light. All the other particles are very well described by the Bethe-Bloch formula. We consider multiple ionization measurements. Those are usually done in gas detectors. For example, in drift chambers, or more impressively, in fact, in time projection chambers. It has been tried to use multiple ionization measurements in tracking detectors with silicon. Atlas tried, CMS tried, but it did not help a lot. So gaseous detectors are the tool of choice for the EDX measurements in high energy physics experiments. At least the main cases, the prominent cases are all time projection chambers and other gaseous detectors. The measurement of the ionization is done at the same time as the measurement of the particle track is done. What is done in a TPC, the track is followed through the whole detector volume, the momentum is measured, and the energy loss is measured at the same time. The discrimination is then easily done at low momentum, where the 1 over beta squared range of the Bethe-Bloch formula is dominant. Let's look at the top right plot. That is the DEDX. This steeply declining energy loss as a function of the particle momentum for the different species, that gives the separation power at low momentum. Because for the same momentum and different particle masses at the lower momenta, the EDX depends on beta, depends on 1 over beta squared, and beta differs for the same momentum for the different particle species. The energy loss is completely different. So if we want to do, again, pion-kaon separation at low momenta, and we see an energy loss that's consistent with a pion, we can be very sure that that was not a kaon, at least. The important factor that enters the quality of that enters the separation power of the EDX measurements is the difference in the mean energy loss. For example, for pions and kaons, you need to compare this yellow contour with the blue contour here. The EDX measurements extend to higher momenta because the logarithmic rise that we've discussed in the derivation of the Bethe-Bloch formula differs for the two particle species. The plot here in the middle shows the difference of the mean energy for pions and kaons. It has a minimum here around 1 GeV. This is where the yellow curve and the purple curve intersect. At the momentum of 1 GeV, nothing can be said, but at higher momentum, we see 20% differences. This is in relative units. So we have a 20% difference for 5, 10 GeV, and we can say probably something up to 100 or so GeV. So the EDX measurements are suitable, for example, for heavy ion collisions at the LHC. What we show here is what we've briefly discussed again already in lecture 3. This is the Alice TPC, the time projection chamber. It reads out the whole event. In that case, it was a lead-lead ion collision, and all charged particles momenta are measured, and at the same time, their energy loss in the gas of the time projection chamber, which was a neon CO2 gas mixture. We already discussed this. So I think you're experts in TPCs. I've also already highlighted the diagram to the right, which shows the momentum versus the energy loss in the Alice TPC, and we beautifully see the different populations. And that's the low energy regime, where particle discrimination also for very heavy, in this case, antimatter hadronic bound states can be done with excellent resolution. We have here deuterium, tritium, antihelium-3, and even antihelium-4, which I always highlight because it is particularly impressive that we have antihelium-4. The spread in the populations that's indicated by the arrows, that's what limits the particle identification. If this is a narrow and precise measurement that is, for example, not subject to lambda fluctuations, then we can carry out the separation up to high energies. If it is wide, then the resolution degrades. Okay, that's how time projection chambers work. Another interaction of particles with matter that was dependent on the velocity was the Cherenkov threshold. A charged particle traveling in matter of a refraction index of n with a velocity that's larger than the velocity of light in this material emits Cherenkov radiation. We've derived a few general properties in lecture 3. Cherenkov light is a weak source. The signal is typically only 0.1 to 1% or so at most of the ionization. If you recap from lecture 3, the Cherenkov angle is 1 over beta n, and if the particle moves with the vacuum speed of light through the medium, then the maximum angle that the Cherenkov radiation can be emitted under is given by the inverse cosine of the inverse refraction index. Cherenkov radiation is only emitted above a certain gamma value. That's the vacuum gamma. That's the vacuum relativistic gamma of the particle traveling through the matter, and it must exceed the threshold value given by the refractive index here. The radiation is emitted in narrow rings. You see from this formula that if you want the low threshold, so if we talk about low momentum particles, then in fact you want a high refractive index. A high refractive index means that the medium speed of light is low, and hence you easily exceed the threshold. Now, for low momentum particles, we have time of flight and the EDX. Now we talk about high refractive index. For a high refractive index, we want in fact values that are close to 1 with a high threshold, because then we can by making Cherenkov measurements in sequence with different refractive indices, we can differentiate the particles. So we actually want, for Cherenkov counters, we want refractive indices that are fairly close to 1. Then the threshold of Cherenkov light will be high, and then we can get discriminative power for high values of gamma. The Cherenkov counters only detect the photons of the Cherenkov radiation. Cherenkov counters disregard the spatial and the spectral structure of Cherenkov radiation. The principle is like this: a particle goes through, for example, gaseous material, emits in a narrow cone Cherenkov radiation that is reflected, and a light guide is used to channel it towards a photomultiplier. If a signal is found, then you know the gamma value of your incoming particle was higher than the threshold computed from the refractive index of the gas used in the detector. Let's look at a few examples of Cherenkov detectors. The sketch here shows the Cherenkov detector from the Tasso experiment. The Tasso Cherenkov counter achieves proton-pion separation by using 3 materials. There is an aerogel with a tiny refractive index, and then there is Freon and CO2. These 3 gases have different Cherenkov thresholds, and a particle that's going through may or may not emit Cherenkov radiation. That is then, there are mirrors inside here, that is then mirrored towards photomultiplier tubes, which record these individual photons as the particle traverses the detector. These are typically large detectors. You have to operate several. That means you have to operate several gases, several temperatures, pressures, several types of photomultipliers, because they need to be sensitive to different wavelengths. So all in all, these are complicated detectors. Let's look at what materials can be used for Cherenkov threshold counters. It all depends on the refractive index. The media to the left are solid state materials or liquids. The medium to the right are gases. Gases have the smallest refractive indices. These are really tiny, CO2, for example. So we talk here about differences to 1 of the order of 10 to the minus 4. For liquids and and solids, the differences are much, much larger, 3 orders of magnitude. So there's a very large gap in between the refractive indices of solid state materials and so solid materials and liquids of 3 orders of magnitude. There is aerogel, which is a very light nanoporous material. It's made of silicon oxide and water that can be assembled with various densities, and it hence fills the gap between the refractive indices of solids and liquids and gases. This aerogel can be manufactured in densities such that you can really interpolate the refractive index and fill the gap that nature has left here for us. It's a the picture to the right shows aerogel with 3 different densities. The density is almost 0. It's extremely light, and it can be manufactured with different refractive indices in that gap, and that is also the reason why it was used in the example below here in the initial one, in the initial Cherenkov counter in the Tasso experiment. Okay, so much about Cherenkov counters. A famous and spectacular detector are the ring imaging Cherenkov detectors, so-called RIG. A RIG use also the information of the angle of the photon emission. Look, for example, here there is a Cherenkov liquid radiator, a thin layer of liquid, particle is going through, and because the refractive index is large, the emission angle is large, and a Cherenkov ring is projected on a photodetector. Now, the photodetector itself, when the particle goes through, has a finite refractive index. So again, Cherenkov when it goes through the photon detector, it enters a gas volume with a gas radiator, and then Cherenkov light is emitted that hits a mirror, and the ring is reflected from the mirror back to the UV photon detector, and hence the defining signal of a particle going through are 2 rings, and the size of the rings are indicative of the particle's velocity. And by measuring the size of the rings, one only needs a fraction of the arc. One does not need to see the full arc. The particle momentum, the particle velocity can be computed. This dual rig system that's shown here have been used in the Delphi experiment. So look at this gray detector here. There's a TPC below, and then there is a barrel ring imaging Cherenkov detector. Particle goes through here. There is a liquid radiator here. The first ring is emitted on the photodetector, and the second ring is emitted when the particle traverses a gas-filled volume. And here you can see the mirrors that reflect back, according to this principle, that reflect back the second Cherenkov ring on the photodetector. So if you see 2 rings side by side, you know that a particle has gone through. I find this an impressive construction. Simply, it's great. It's not. It does not tolerate high occupancies. You cannot have your photodetector completely filled up with rings. You would no longer know what is what. But in terms of detector physics, a ring imaging Cherenkov detector is actually impressive beast. Let's look at the contemporary one, at least the sketch. These are the LHCb ring imaging Cherenkov detectors. Again, aerogel is used. There are two ring imaging Cherenkov detectors in LHCb. One is very close, the left one, RIC1, is very close to the interaction point. Particle goes through this layer of aerogel. A ring is emitted around the particle track. The particle goes through the mirror. The ring, in fact, is reflected and recorded at the photodetector. And similarly, a CF4 ring imaging Cherenkov detector, much further away from the detector, is located to provide further information on the Cherenkov radiation emitted by the particle and thus on the velocity of our candidate. And from the velocity and the momentum measurement, the mass can be inferred, and from the mass we know what particle it was. Yeah, maybe a detail. Hybrid PMTs were used, these photomultipliers. That's the detectors that are used here in the LHCb rig system. These are large hybrid silicon devices. So a photon hits the optical window, an electron is emitted and is accelerated towards a silicon sensor. And the assembly is such that the position resolution is resolved. So if a ring of photon hits here, you're going to see a ring of photoelectrons on your sensor. Good. There was the ring imaging detectors. Impressive, expensive, special purpose, and used in fixed target experiments or in low occupancy collider experiments. The next physical process that we've already discussed and that we can exploit is transition radiation. Transition radiation, if you remember, is the radiation, the photon radiation, that's emitted when a particle with high velocity moves from an area with a refractive index of N1 to an area with, in this case, higher, I believe, yes, higher refractive index N2. In this case, the relativistically contracted field lines in matter rearrange, and that rearrangement causes the emission of photons. The total emitted energy from transition radiation is proportional to gamma, and gamma depends on the velocity. So when the momentum is known, one can infer the mass. It is only relevant for the highest values of gamma above 1000, and these high values are more likely to be achieved by electrons and positrons. So transition radiation is indicative of electrons and positrons and is suppressed for heavier charged hadrons, for example, pions. In this, thus, this detector can discriminate between electrons and pions. The numbers of photons, however, is really extremely small. Typically, one transition region is absolutely not sufficient. A frequently used geometry, therefore, is a layer of foils. So we have foils with different refractive index, and a light candidate particle with high energy penetrating. And from the rate of the presence of transition radiation, we can get information on the particle mass because we can infer the relativistic gamma. The angle of the emission is very small. It is 1 over gamma. So if it's 1000, then this is really extremely collimated radiation. The photons therefore travel extremely close to the track. What one famous application is the transition radiation detector on the AMS experiment, which is mounted on, which is at the International Space Station. There, it is all the energy is produced with well, the energy that's used for this experiment is solar, so one cannot tolerate high currents. These are not available. But one can have high voltages. What is done here is a xenon Cu2 straw-like gases detector that creates avalanches, and the xenon is a photo sensitive add-on to the gas. Hence, a photon that's traveling through may create a transition radiation signal. The track is known because there's a tracking device in the with the AMS detector, and the proton-electron separation is performed by this combination of a fleece radiator that creates the transition radiation, and a gases detector with a photosensitive add-on to record the transition radiation photons. That's what is done in space. Let's look underground. Atlas also has a transition radiation tracker. I mentioned it before. It is a straw tube transition radiation tracker, shown here in these yellowish straw tubes. It's a xenon-based gas, 4 millimeter in diameters, and there are 30 micrometer wires inside. A similar detection principle as on the previous slide. So that detector aims to separate electrons from pions. The electrons are lower in mass, therefore with the same momentum have a higher gamma factor, and when they travel this straw tube tracker, we get the measurements, we get the tracking measurements for the pions and for the electrons, but the electron will also produce this transition radiation signal along its trajectory through the tracker, and thus one can discriminate electrons and pions. Okay, that's the Atlas transition radiation tracker. Here's its performance. This diagram shows, it's a detail. It shows the efficiency of, it's a misidentification efficiency of pions. And without the transition radiation, one has a 10% or so misidentification. That is, in 10% of the cases, when you think you have an electron, you actually have a pion. With the transition radiation measurement, one gets the squared, one gets the black squares, and there's a factor of 10 in between. So the pion background to the electron identification is reduced by a factor of 10. Okay, that's what I wanted to tell you about the identification of particles. Let me pause the recording.